I have a problem. How do you visualize 4 dimensions and above? Well, normally you can't, or it's not that straightforward for novices like me. But one can at least try. So, there are some rows of data that I would like to visualize. Some are 3 plus 1D and some are 8 plus 1D. I say 3 plus 1 or 8 plus 1 instead of 4 or 9 because the plus 1 part actually indicates that it is the last column where the resultant metric such as total score rests in. I can easily do this for 3D, but the challenge of dealing with hyperdimensions still remains the same. Yet, this leads to one big issue. What axis or dimension will I use for the output variable? But first, what are we? Personally, I think we are 3D blobs at the mercy of flow of time, the closest thing we may perceive as the next dimension. So, what is a dimension? Well, for now, let's call it something next to which we can put an axis in order to represent it. For example, in 1D, we can have an axis with numbers for us to give meaning to them and analyze. In 2D, we can have an x-axis and an y-axis to create a 2D plane so that objects may be mapped or progress over time can be shown. And in 3D, we can have axes x, y, z to have a cube or imagine a cube on a screen. But 4D and onwards, even when we're imagining the 4th axis, it is not easy to decide how it should be placed. Tricky, eh? I know there are various ways of doing this. Many greater minds have worked on this issue, and there are already so many tools in popular computer languages such as Python. UMAP, Tisney, and PCA, just to name a few. These methods lose some of the columns, favoring only a select few over others. But I don't want that. I do not want to sacrifice any columns or dimensions for the sake of others, mainly because I'm assuming that what matters will keep changing and that I may never know what will be more important. What is the real problem? The real problem is that our cognitive capacity and technological ability to represent and comprehend 4+ dimensions is more lackluster than how much we are so familiar with doing so for 3 dimensions. Why? Because we are 3D beings and we have only 3 axes that we can manipulate and traverse. No matter what we do, we cannot see, sense, or map beyond the 4th dimension without losing one of the pre-existing axes, namely x, y, z. If I choose to lose no columns, I'll lose everything, because seemingly I cannot visualize anything. I am going to break a rule. What if I decide to lose a tiny bit of everything, as in some level of distortion on all parts of the data, just like suffering random pixel losses in this image of the matrix, to keep everything? I'll be treating all columns equally, and this way I don't have to lose some columns in their entirety. This approach does sound like the exact opposite of what other methods, PC in particular, do. But since I've declared my intentions, this is what I will do. A live together, a die together policy for the dimensions. So really, what is a dimension or an axis? What are the characteristics? Amongst many, we may say perpendicularity. With perpendicularity intact and in our mind, let's break down how things work in 2D. Imagine some points on an xy plane, 1, 1, 5, 3, 2.6, 1.2. But these aren't just mere coordinates, they are also vectors of length 2. Now, here's a unit circle with its infinitely many unit vectors. Of these unit vectors, let's take 2 for now, 1, 0 and 0, 1. Having had a look at the xy axes, we may say that these 2 unit vectors are acting as the axes, sort of like axis vectors. Let's see them in action. For point 1, 1, its first element of point pertains to the x-axis, whereas its second element pertains to the y-axis. And given the two unit-turned axis vectors, we can see that the point is just a sum of two scalar vector multiplications involving the axis vectors. The same may be said for the second point 5, 3 and the third point 2.6, 1.2. In other words, the coordinates on an xy plane can be expressed in terms of two unit vectors. What a waste of effort. Nothing's changed. What we actually did was investigate how the coordinates of an xy plane can be expressed in terms of two unit vectors that are perpendicular. In fancier terms, linear independency holds true in this setting. This is a rule. Since I already decided to break one rule, let's break this one too. What if perpendicularity didn't have to hold, and we decided to have every dimension on the xy plane? This way, we can fold dimensions and squeeze in the axes. Then I don't have to rely on methods of dimensionality reduction. I can use the data in its entirety. Here we have back the unit circle and the two unit vectors. Let's add two more unit vectors to serve as axis vectors in the first quadrant of the xy plane. But, at the risk of sounding whimsical, I declare that I will treat every column/dimension equally. Shouldn't that mean the axes have to be spaced out evenly, like this? This is supposing that we'll never know which axes are more important than others. The squeezed and renamed axis vectors on the 2D plane have three identical angles in between one another. The values of these axis vectors are combinations of results from trigonometric functions cosine and sine of the angle D, where D equals 30 degrees or pi over 6 radians. We'll observe how all possible binary vectors of length 4 and the four axis vectors work in tandem, given D equals pi over 6. Each element of a vector will be applied as the scalar to the axis vector in its corresponding order. The result of all the scalar vector multiplications will be summed up to become a vector of length 2. Let's watch. These binary vectors of length 4, after transformation, will occupy these points on the xy plane. To generalize, we may say that we just performed a vector matrix multiplication, given a vector of length 4 and a matrix made out of the four axis vectors. And this is a more generalized version where V is a vector of length n and A is an n by 2 matrix, and the summed result is a vector of length 2. This works for cases where n is larger than 4 as well, as we see that all binary vectors of length 8 occupy these points in similar fashion. And when vectors to be transformed consist of not bits, but some more digits, they may still be successfully transformed, albeit in a more compact pattern. It is also possible to get a glimpse of how the shape will be when the number of possible dots is astronomical because n is simply too large. This can be done by computing only for the vectors that would result on the outermost rim. This will reveal a lens-shaped silhouette or a vesica piscis within which all the other possible points would exist. Something interesting happens when we treat the transform values as vertices and connect them. Not surprisingly, we see a square when given vectors are 2 bits long. And it's not that difficult to see a cube when n equals 3. And along comes a 2D projection of a tesseract. Finally, this is what a 5D cube would look like on a 2D plane. You might be curious as to why I'm doing this. I have data from millions and millions of chromosomes of length 100 from my genetic algorithms experiments. One day, I needed a way to visualize the progress of these binary vectors as they evolved throughout the generations. I could have resorted to other methods, but somewhat knowing that randomness is the core of genetic algorithms, and it is what drives evolution, I was ironically confident that I'll never be confident about which genes will be more important than others. Therefore, I do not want to lose any aspects when visualizing. So I needed a technique to compress all 100 dimensions into 2 dimensions in order to have the z-axis freed up for the fitness scores. The transformation demonstrated so far does exactly that. And now that I have a robust, compute-light way of projecting hyperdimensions onto a 2D plane, I can do this. Thanks for watching.